So the ultraviolet catastrophe, you can read, refers to a disagreement between practical measurements of the energy intensity emitted from what's called a black body. Now, a black body isn't necessarily black, but it emits all wavelengths. It absorbs all wavelengths as well, a black body. And the fact that it absorbs all wavelengths makes it, the name makes sense, because anything that's black will absorb all the different light waves that land on it. But a black body actually absorbs every electromagnetic wave that lands on it. So radio waves right the way through to X-rays and gamma rays and stuff, all of them are absorbed. And of course, when you heat something up, it starts to emit waves, and you can get just electrons moving backwards and forwards in wires, and that will emit radio waves. If you get something hotter, then you can get the particles in it to jiggle, and the accelerations there emit infrared rays. If you get it even hotter, it will start to emit visible light. So you've got this scale where you've got charged particles accelerating about, changing energy levels, and you end up emitting waves, okay? Now, the ultraviolet catastrophe says that the energy intensity of the different wavelengths from a black body, if you use classical physics, the energy that comes out should get bigger and bigger and bigger and bigger as the source of the energy gets hotter and hotter and hotter. I mean, it never comes back down. And so classical theory gives you this weird line. Okay, so here the observed spectrum is the one that's dotted. That's what we actually measure. But classical theory says that it should just keep going up. So as the wavelength gets shorter and shorter and shorter, you get more and more and more intense waves coming off, and that's what classic. And this is mostly in the ultraviolet, which is why it's the ultraviolet catastrophe, because it doesn't fit with the facts. So there's something really wrong. Okay, so a black body is one that emits all wavelengths. The dotted line shows the practical variation of energy intensity emitted at different wavelengths, with a wavelength lambda for a particular temperature. Okay, the solid line shows the prediction made using classical physics. This predicts that most of the energy would be emitted at the ultraviolet wavelengths, and would become infinite at very short wavelengths. Measurements indicate, however, that there is a peak. Okay, it says as shown by the solid line. It should be as shown by the dotted line. That should because there's only a peak in the dotted line, so that should say dotted. Okay, this peak occurs at shorter wavelengths as the temperature increases. So that's Wien's law. So you get this going on. So it's as it cools down, the peak moves to the right. Okay, so and moves to the left. So shorter wavelengths, higher frequencies, at higher temperatures. So this is T1 is higher than T2. It's higher than T3. Okay. And so on, right? Now, the dotted line and the pink ones that I've drawn, that is the observed black body radiation for different temperature sources. The solid line is this classical prediction, and you can see that they don't tally at all. In this ultraviolet region, the classical prediction is basically infinity. It goes off up here, and that's not what we see. So any theory that we come to explain the observed black body radiation has to explain why this ultraviolet catastrophe doesn't happen. Okay, so let's clear all the drawings. Okay, so now this problem was resolved by Planck. Okay, so he was of Planck's constant. Yes. So he is really the first person to talk about this quantization, in this case of light, electromagnetic waves coming in lumps. Okay, and so Planck suggested that radiation is emitted in these quanta, which we now call photons. This is why it's a turning point in physics, okay, because the energy comes in lumps, quantum of energy. Okay, so the quantum is related to a single frequency, and this is Einstein's equation, this one, which because of this equation, Einstein's equation is also hc over lambda. Okay, and I suppose I ought to put a pH there because it's the energy of a photon, a single photon. Okay, so Planck said the quantum is related to a single frequency, and energy quantum is HF, so the high frequency radiation is emitted in larger chunks. Okay, so it says, using the idea of energy quanta as packets of energy, Planck was able to develop a theory to explain the shape of the observed spectrum. The proposition by Planck also laid the foundations for other areas of physics where classical physics was failing failing to explain what was observed. And photoelectricity was one phenomena where quantum physics came to the rescue and solved it. Now, I read that and I went, how does the coming in lumps work then? That doesn't make sense. What is it about energy coming in lumps that means that it solves this catastrophe problem? Because it seems to me that this doesn't explain it at all. So I went looking for a better explanation, and I did find one. This was on a website called Stack Exchange, and the person who asked the question, it was I've searched around the site looking for older posts. For a bit of background, high school student, I don't have a great understanding of more advanced physics, okay? I understand the concept of black body radiation and how classical theory leads to the UV catastrophe. I also understand the implication of quantization of energy and the basics of the quantum model of light. In other words, the photon, and they're aware of the photoelectric effect. However, the one thing that I'm struggling with is how exactly Planck's assumption that the energy is quantized solved the problem, which was exactly what I thought when I read this, that the teacher's notes there. So why it is that when we assume energy is quantized, we can now predict black body curve perfectly. Logically, what changes in our understanding of black body radiation? Okay, so, and this answer seemed to me to be a very good answer. So it was, I'll aim for an intuitive explanation of how quantization can solve the ultraviolet catastrophe and let others provide accurate formulas. Okay, so this is this is as far as you need to go from the point of view of the AQA A level. Right, if I just scroll, can you see there's all these equations? You don't need any of it, okay? So let's have a little look at what it says. The ultraviolet catastrophe says that a black body would radiate energy not just around a given average wavelength, but also in all wavelengths. This is the problem, especially very short ultraviolet wavelengths. And because these wavelengths are very energetic and there is no limit to how short you can make them, okay, the black body also radiates in, a wavelength divided by 2, or the next one divided by 2, divided by 2. There's no limit on how short you can make your wavelengths. Okay, so the total amount of energy that would be produced is infinite. That's the problem. That's the problem. Okay, so how does quantization solve this? Well, basically it says you can't radiate less than a quantum of radiation in a particular wavelength. This is this idea of energy coming in lumps. Okay. According to Planck's quantization formula, which is E is equal to hc over lambda, that's hf, right? A very short wavelength has a very large quantum energy. So if the would-be radiation predicted by the black body formula is large, but not as large as this single quantum, no radiation would be emitted by that process, because it's not as big as a single quantum of energy. And as you go down in wavelength, up in frequency, the energy packets get bigger and bigger and bigger and bigger. And if you haven't got a whole one, you get nothing. Can you see that that is solving the problem? So in our case, in a black body in thermal equilibrium, only a tiny minority of the atoms, or whatever it is that's got the energy, have very large energy. And only those could possibly radiate some of their energy as one or more quanta of very short wavelengths. All the other atoms will radiate zero of their energy at those short wavelengths. Zero, because they don't have enough energy to fill up, if you like, one whole quantum. Okay? So you get nothing. Just like with the photoelectric effect, if you are below the threshold frequency, you get nothing. Okay, all the atoms are basically got less energy than is needed to provide the energy for one quantum of light energy for these very short wavelengths. So you don't get any, none. It's not that you get a few and it's tails off or something. You get none. So all the other atoms will radiate none of the energy at the very short wavelengths. All in all, the amount of energy radiated in the very short wavelengths will be very small, approaching zero as the wavelength gets shorter, giving the familiar bell-like shape of the black body radiation curve instead of the infinite ultraviolet catastrophe. Now, I hope that I've explained that well enough. In fact, in the OCRB course, there is Boltzmann distribution, which tells you that if you've got a gas, I mean, it could be electrons as a gas, but yeah, a gas, some collection of particles with a certain temperature, you can predict how many of those particles will have more than a certain energy. And the bigger that energy, the smaller the fraction, and the fewer particles there are going to be. So for any given temperature of a collection of gas particles, for argument's sake, only a small fraction will be above that threshold. And of those, only the ones that have got enough energy that they can make a whole quantum will emit any photons of that energy. And because there's so few, not very many get emitted, which means that you end up with this complete drop-off to the left of the increasing. I mean, it looks like it's an exponential increase, and then you get this proper drop-off, don't you? If I go back to the go back to this curve, you see it looks like it's exponential, and then you get this proper drop-off because there aren't any particles in the hot object that are energetic enough to produce a wavelength that is short enough to produce a whole quantum. And that's why it just drops back down to zero. Yay, we solved it. I hope that that's clear. But that's how this quantization of light solved the catastrophe, the ultraviolet catastrophe.